Mines Dhanbad in 2009 and 2013 respectively. His research interests include wireless sensor networks, cognitive neuroscience, brain-computer interface, and medical imaging. He has published more than 160 research articles in reputed international journals and standard conferences. The publications include reputed journals such as ACM Transaction, IEEE Transaction, IET, Elsewhere, Springer, Taylor and Francis, and Wiley. Society and also received several awards such as Young Faculty Award, DKIF Best Researcher Award, Asia Arab Distinguished Faculty Award, CSIR Senior Research Fellowship, Dr. APJ Abdul Kalam Lifetime Achievement National Award, etc. Journals. He has also published 4 books by reputed publishers such as 𝗙𝗍𝗃 Press, Taylor and Francis, etc. He has handled various administrative positions such as Head of CAC Department, T&T Officer, First Appellate Authority, Senate Member, AAC Member, and Member of Board of Governors, etc. at NIT Goa. Dr. Reddy delivered guest lectures and keynote talks in more than 150 institutes across the country. 6 of his PhD scholars have been awarded doctorates. Another 12 PhDs are ongoing. It is a privilege to have you with us, sir. Over to you, sir.
Yes, thank you. So good evening, participants. This session we are going to discuss on the various machine learning challenges, particularly in the domain of human-computer interaction. Then we are also going to see how various existing machine learning tools can be used for this stated problem. Let me share my slides. Please confirm upon shared. Can you see the slides? Please confirm.
Yeah, it's visible, sir.
Yes. So please let this session be very interactive so that I can clarify if you are in doubts. So now I'm sure many of you are doing research in your respective areas. Now tell me like when you began your research in any of your domains, like what is the first problem you have faced? Like somebody is in cloud security, somebody is in sensor network, somebody is in security, information security, somebody is in blockchain, many other areas. So what is the first problem you have faced whenever you select any research topic of your choice? Tell me. Please be interactive. Huh? You are not faced any problems when you started with
Sir, to understand the
problem
topic.
statement. Okay, you understood the topic. That's eventually needed. But
Sir, to
when you
understand the
get into
topic.
actual problem statement, you have selected a problem statement, right? That's fine. That is the first, first and foremost thing you have to do in any of your research. Next, what you will do once you select a problem statement, what is the first challenge nowadays many of the researchers are facing? Tell me, isn't it collecting data? Like I want to get some data for my problem. You all agree with me? You all agree?
Yes, sir, we do agree.
Yes. Now, if you go with many of the problem domains, the first problem any of the researcher faces like getting the data. Data acquisition itself is the major challenging problem we normally face in this. But here it comes to this particular domain where we are going to see a lot of machine learning applications involved in. The first availability is the data. Like when it comes to human computer interaction, like first I'm going to go what is human computer interaction. Let me make you understand. Then we'll go into various problems. Then we'll jump into various machine learning tools where and all we can use for this human computer interaction. Now let me go back. Like availability of the data is one of the common problems that we normally face in any research area. When it comes to the domain like human computer interaction, where heavily, very sophisticatedly, we are going to use a lot of artificial intelligence models. Here, the availability data is first in hand. Then we are going to think how to frame the problem statement, or you can say how to use the data for the selected application. Now, what do you mean by human computer interaction? Like you say, like now we are going to make an interface. By name, it's a we are going to make some communication, some interface, some kind of medium between a computer and some part of human body. When we refer as a whole human, like some part of the human body, we are going to refer it. So here, what we are going to do, by making such an interface, by making such a connection between two objects, one is the human side or some part of the human body, other is the machineries, maybe a high-end workstation or a high-performance computing server or a small computer, according to the needs of the application we are going to investigate. We are going to generate a lot of data. When it comes to data, whether it comes from the like human to the computer or computer to the human, like when we say. Now, most of the research going on in this domain, human computer interaction, mostly as of now, like a lot of focus is there from what getting or collecting some data from human and store in a workstation, then use some sophisticated tools to process, analyze, understand, and make some knowledge discovery from the data which you are collecting. In this process, we are going to use a lot of machine learning model eventually. Even in fact, in data acquisition process, we are going to use, of course, for filtering, feature extraction, and all. So first of all, when it comes to like when we look into this, growth of this domain over the last 10 years, maybe a decade or maybe slightly more than that, and what about the future? No, this domain has been focused a lot over the last 10 years, maybe a decade time, and it is going to have a lot of scope for next 2 to 3 decades. Next 10 years, you can see excellent growth it is going to have, like, because a lot of medical and biomedical signal processing applications we are going to investigate here, and a lot of healthcare technology system we are going to develop, and a lot of biomedical and a lot of this forensic application we are going to develop. Even beyond a lot of IoT applications we can have. We are going to see each one of them. Don't worry. We're going to see each one of them. So when it comes to the human-computer interaction, like I mentioned, the ultimate purpose is like collect some type of data according to the type of application we are going to investigate, and then we are going to see what machine learning model, like which type of model we are going to really need for the selected application. Then, like mostly, like we are going to see, like it's like a modeling and simulation of this particular interactive system, and how to solve the suitable problem statement for this. So normally a lot of challenges involved. It's not so simple like we're going to connect an electrode wire and grab some data from the users or people. It's not so easy. There are a lot of protocols and everything we need to follow. This domain is some different when it comes to other domains. Like we have to know a lot of experiment protocols, some ethical committee approval, a lot of things I'm going to discuss in next slides. So when it comes to the human computer interaction, our job is like how we are going to design such a human computer interaction system. And once the experimental design is over, once the data is collected in an interactive manner from the user to the computer or a workstation or high-end machine, and once the data is collected, put in the desired form, then we are going to see what are all the useful interdisciplinary applications we are going to perform. Various psychological applications, socio-psychology, sentiment analysis, plenty of applications we are going to perform. So like I already mentioned, the dominance of this domain, it has a lot of interdisciplinary applications, neuroscience applications, psychology, healthcare related, and some anthropology applications, sentiment analysis, like a sociology, philosophical applications, linguistic, analytical processing, natural language processing related applications, artificial intelligence, other related applications. Plenty of applications it has actually. We are going to touch upon at least 10 applications, and we will be looking into how we are going to use various machine learning model. Before that, what are the various components in human-computer interaction? And of course, many of you already started doing research. Some of you are heard about this, and some of you are new to this domain. So when it comes to this, the 3 components we have to really learn about. For that, please confirm, am I audible?
sir.
Am I audible? Hello?
Sir, you are audible.
Shubham, can you hear me?
Yeah,
Yes,
we
yes.
can hear you, sir. You are audible. You are
Yes.
clear, sir, not an issue.
Yes. So when it comes to the components, like first of all, like we mentioned, there is an interface between a human and a computer. And our job is to identify how this interface can be established. The interface which you are going to have for certain problem statement or certain type of application is not same for every similar one. No. So how we are going to make the electrode connections, how we are going to make the, these data acquisition tools to be used, and how we are going to record the signal, and what are the trials we are going to perform, how many subjects, and then channel selection, and plenty of things we need to identify. They vary from a problem to problem or application to application. And our main job of any human computer, now whenever I talk about developing or designing a human computer interactive system, is that is just how we are going to make such an interface which will give you the desired data that is collected from the suitable part of the human body. Then it comes to the next level where we are going to make the noise discovery from that. So you see, it is not the job of human computer interaction for analytical processing mostly. It is mostly for what you can say getting the data for recorder purposes, and then we are going to make further analysis by exploiting all these suitable machine learning model. So here the goal of main human computer interactive system is how we are going to effectively make an interface between these two the components, and then like we say human and computer, the interaction of it is possible by making a possible interface. Then we are going to understand how to use with the data that is captured, and it changes now. First of all, like why do you need to understand humans? Like already it is by default answer, like we say when we are going to applications like some psychology, cognitive analysis applications, and then mental state analysis, human contemplation, and plenty of other applications related to human data. Obviously, like, if you can see wide variety of applications we can develop just from human. Like if I take some EEG signal, I can make some his mental state analysis, human contemplation. If I take some ECG data, I can see his like heart rate prediction, or you can say any spikes that are identified in the ECG signals, and then we can see like early prediction of heart attacks, and then we can talk about recurrence of cardiac arrest, and then many such applications. Just 2-3 sample I'm referring. Similarly, you can imagine if I'm going to have such an interaction with wide variety of components in the human body. Whenever I refer component, maybe a part of the human body, you can assume. So when such a large and wide variety of data that can be captured from the human body, now people say cost of the human body is billions of dollars. When they say when we can get such a large amount of, or you can say wide variety of data, maybe it's a diabetic retinopathy data, some electron-encephalic signals, brain signals, or ECG signals, or fMRI, CAT scan, PET, many type of PT signals. Plenty of signals are available from one human. Hundreds type of different signals are available. It depends on what type of human computer interactive model we are developing or designing, and for what purpose we are, or you can see which application we are going to investigate. Then how the interface is established, and how much amount of data is required from how many subjects, and then how we are going to analyze further in the next level. So obviously it is very obvious to see that recording such signals or data from humans, we have plenty of applications. Now, I have given at least 10 applications in this slide. Now, the same whatever I explained. When it comes to interface, it is very important. Application to application, how a particular system, sensory system, and then how a particular channel connection, and then electrode wires, and then this everything, the entire interface components, how we are going to define, they are very important. A set of hardware devices and software tools, everything we call as an interface. When it comes to brain vision, brain data, we're going to talk about like brain vision recorder and analyzer, either purpose for recording and analyzing, or pre-processing, or noise removal techniques, etc. I've already talked about the basic goal of human-computer interaction. Now, I think you must have understood at least the basic purpose of human-computer interaction. Now tell me let me make some small question answer session. No? What is the main purpose of this domain, the human-computer interactive system, or human-computer interaction? Now tell me. What is the main object of this one? Tell me somebody. What is the main objective of this domain, human-computer interaction? Now we are going to machine learning side. Tell me when machine learning starts, when we get data into our hand, right? So now main objective of the human-computer interaction is we already developed an interactive system to collect the data. I've already chosen my application. Then I collected the signal. Now I'm going to talk about the suitable application. Right? What are the possible application now? When it comes to the researcher's point of view, when such an interactive system is possible to make some communication between a human or human component or body part to a workstation, it has become like people started thinking about like, can't we, make some highly sophisticated applications by, now see, first of all, you have to be very clear that the kind of application which you generate or which you can provide from other domains, they're not same like this one. The impact or the influence of this particular research in this domain is very, very vast compared to other. Can you imagine like, can you compare developing a simple some encryption protocol or some kind of ciphertext generation model or some small security application to a human computer interactive model where I can use somebody to identify whether he's lying or not, or whether I can know somebody's ATM PIN number without asking them. Such a level of comparison we have when we're going to talk about the type of application we can derive out of this domain and other conventional domains. That's why this domain has been, focused a lot for the decade of time. So when people started understanding this human computer interaction system, they started thinking like crazy about all these controlling the real-time world with this human data. When we say controlling the physical world with our thoughts, means they are going to take some data. Now with the development of Internet of Things, from computer networks to adapter sensor networks to IoT, whatever. Now people started imagining like how I can control the data without moving from my chair. So there are a lot of options have been seen with the introduction of this human computer interaction. Then people started developing a lot of commercial BC applications and other HC applications, and then some wearable devices for some gaming application, virtual reality, augmented reality type applications and all. So how they are going to see now when it comes to the applications like from this domain. Now when you go to machine learning side, why this particular let it be a case study like brain computer interface, one of the very popular well-known human computer interface system, for example BCA. So in the BCA, when we talk about like what is so important in, or what are the major advantages of taking up this domain, the reason is, if you can talk about the artificial neural model, when we talk about simple neuron, artificial neural model evolved from a biological neural model. Now, if you can see, they are ruling the computing world now. The artificial neural model, the basic conventional perceptron model, feed-forward networks, deep learning, extreme learning machine, and then other convolution neural networks, recurrent neural networks. If you see, just its variants a lot. Just when you observe how a biological neural model works, how a neuron cell communicate each other, and then how a signal passes, and how an action potential is generated, and how this dendrite communicate, and how the cell body, make this neuron works, how the nucleus of cell body is defined, everything, all these things. So just by understanding the biological neural model, when people develop such artificial neuron model, a basic simple structure, its variants like it has gone to such a level of computing speed where you can't imagine. Now they are ruling the computing world. Nowadays, out of the 10 computing, almost 6 to 7 are being solved with the help of neural networks. Therefore, people started, like people say, humans are always very, expectations are always high. Very, you can say, when they cannot remain satisfied with the performance of artificial neural models, which are evolved from the biological neural model. They wanted to even go to next level of computing. Then they wanted to see, okay, not just capturing the behavior of a biological neural model and develop such a computing networks using artificial neural network, Why can't we go beyond that? We go into the human brain, understand how it processes, then connect their behaviors and then signals or whatever they is. Then we are going to use such signals to again, I mean, for some computing problems. And then again, you can use these neural networks or any other computing tools. So they wanted to go back to their dream, like I can make things controlled, I can make things understood. All this high-end application they're going to perform. So the advantage is like when we just a neuron to neuron communication have developed such a complex architecture for computing model. Can you imagine the brain which is composed of billions of neurons, a factory of neurons, if you can copy its function, its performance, its computing behavior. If you can understand, see, when it comes to artificial neural network, it is not actually the replicate of the entire human brain functionality. It is only some small component and a small action happens in the human brain. When the entire neural structure in the human brain, when it is analyzed and understood how the complete large, wide area network, which is interconnected with large number of neurons, billions and billions of neurons, how it performs, how it is acting better than supercomputer sometimes when it's faster than supercomputer by say. So you can copy such of any if you can replicate such a complex behavior from the human brain. Then even we can have even better applications. Then people started like more digging more and more into the characteristics of the human brain. Then they started understanding their behavior. Now people may say like, no, we have understood long back the behavior of the human brain and all. What's so important now? But when it comes to the evolvement of neural networks, artificial neural model, and when it comes to the increment of this computing power and the memory availability or memory management technique, with the introduction of this big data analytics, where we started easily handling the percent exabytes of information, people started like expecting more. Then coming into all this developed model based on this computer interface and by just behavior from the human brain captured and then analyzed and then filtered and then processed and then taking further. So this is how people started, capturing the brain signals. Like when we talk about the neuron and neuron to neuron communication, how how it happens, we know. And every neuron, when we talk about, it gets selected from lot of the neurons. Let it be some many other thousands, depending on what action they perform. So when such large impulses are being added and then summed up, or you can say they are identified, now they are finally causing to a particular discharge signal we call as action potential. Thus talks about what is the task that is being performed and how the brain is going to command the various components of the human body. And normally when we talk about the neuron communication using this action potential, the action potential or the electric signal we talk about, their communication is very it's far, very high speed, like it's a lot of miles per hour. So our job is how to develop. Now when it comes to the developing a human computer interactive system, we are going to capture such a behavior. The information processing is at speed or maybe more or less. Then how such a large volume or large number of signals can be captured to indicate the desired behavior for the selected applications. It is not just a computing paradigm which would develop like artificial neural model. It's beyond that. So here we are trying to imitate or not imitating, here we are trying to understand the behavior of the human brain functioning, and then we are going to capture the behavior, and which is represented in the form of some electric signal, maybe some electroencephalographic signals known as EEG signals, and similarly, when you take other case study, maybe ECG, heart signals or whatever it is. Now in this case, we are talking about brain signals. Now, like some prerequisite, when you are talking about such a complex problem, with the help of some brain signals, we have to understand like about the human brain. But of course, in the biology class, I am going to miss that. Am I audible? Shubham, please confirm. Somebody confirm?
Reddy, you're audible. Go ahead.
Yes, yes. So now when it comes to understanding the human brain, now just I'll give a simple example why this domain is completely different from other domains. Now it's not just like collecting some small amount of data and making some small mesh model applied and to make some knowledge discovery. No. When we understand the complete cognitive behavior of the human brain, like the normal human brain, when we talk about, like there are two hemispheres, left and right hemisphere, where each hemisphere is going to be partitioned into four lobes: frontal, occipital, parietal, and temporal lobe. Now, what is the real need of understanding in-depth analysis of the human brain? And what type of, now when we talk about human brain, we're talking about the function of neurons and everything. Now, the major activity is the each component of the human brain is, or each of the human brain is direct, I mean, either hemisphere is for certain task. Like when we talk about front lobe, normally responsible for like planning, or you can say problem solving, decision making, emotional control, etc. When you talk about occipital, it is responsible for the type of task normally, like mainly for processing the visual information. When it comes to parietal, it is for spelling of words, perception modeling, and then when we touch some object, how it is going to react according to the, I mean, the input signals being captured by the muscle receptors. Similarly, temporal lobe, it is for something else, recognizing the faces and numbers and all. And similarly, hearing functions and all. The beauty of this domain, I'll tell you. Now, once I think there is in some United States or somewhere, there was a person who was sentenced to death because he has committed some severe crime. Maybe he must have murdered somebody. Then he was sentenced to death. He was almost about to be hanged. And what happens in the last minute, his advocates, attorney, went to the court of law and mentioned that particular person, there is some problem structure of his front lobe. If you can see the front lobe where it is located in the first human brain, has seen that I mean the advocates MRI images of the patient, not the person who was sentenced to death, not a patient. That there is some problem with the lobe of the particular person. In structure or some component, whatever it is, some kind of structural behavior changes in the frontal lobe. And if you can see, frontal lobe is responsible for social skill, problem solving, and decision making, and emotional control. So frontal lobe is very crucial in controlling the emotions. You can see one key component or key job frontal lobe of the human being. And this particular person, there is some problem in his frontal lobe because of which he cannot control the emotions. That is a point they have raised in the court of law, and they have convinced with the MRI images showing with a normal patient with the frontal lobe images and this particular, and they have taken the, of course, medical opinion, and they have convinced with the person has not intentionally, I mean, committed the crime because he could not control his emotions because there is some structural problems in his human brain with the frontal lobe part. Then they have converted his sentence to death punishment to something else maybe, but he was saved. The person was saved. If you can imagine, see where this cognitive neuroscience application, where they have connected to which particular data and how they have convinced the particular authority to say take a direction. This is the beauty of these human computer interaction models when we talk about now. When we talk about MRI, magnetic resonance, when we say they're nothing but a human computer interactive system, they're coming out. Any diagnosis test when you perform, the result is nothing but what? It is an outcome of the data that is being captured from human computer interactive system. Every diagnostic tool or device which we are using, that's a human computer interactive model type system, right? Of course, but problem is like any such case study when you take it, there's a brain computer interface or ECG related or in diabetic retinopathy, vision related problem, everything. Our job is we have to understand the prerequisite, like when we talk about human computer interaction in the this brain interface, we should know the detailed cognitive structure of the human brain and its behavior, different lobes, each and every lobe, and then hemisphere and the function, everything. Only then we'll be able to manage the front-end application system. And the detailed analysis I'm going to touch upon because it's not a biology class, but you must have convinced with the motivation to the selected problem. Now, the type of data which we normally generate from the human brain when we talk about, normally we have EEG signals when we talk about when the action potential is generated from neuron to neuron communication in the human brain. And similarly, fMRI, when the blood flow, change in the blood flow is detected in the brain activities, and then blood oxygen levels are being identified. Similarly, NIRS data, when the IR light absorption is being observed, and then according to the changes in the light absorption, then we are going to talk about these signals. Similarly, various other types, CAT scan, PET, PHMRI, TMS, transient magnetic stimulation, many type of signals are there. But when it comes to the understanding the brain behavior, most of the people are going with EEG signals because of its accurate behavior that is being captured directly from the neuron communication or action potential, the behavior, and it is actually reflecting the cognitive behavior of the human brain as compared to other indirect parameters like change in the blood flow in the human brain, or you can say IR labs absorption. Compared to that, this digital, or you can say these EEG signals are more accurate in depicting the cognitive behavior of the human brain and its structures. Therefore, people are more, willing to use EEG signals as compared to the other type of signals of the human brain. But there are type of the human, brain data when it comes to. Now, before going further, can anybody say like one, two questions like now I have some this or other fMRI signals or something in my hand. I can form certain application using human brain data. Can somebody any one applications? Whether you use some deep learning architecture or simultaneous or binds propagation, whatever it is, that is different. But coming to this one, can you identify some application by this time? No? Other than what I referred, maybe mental state analysis or whatever it is. Anything else? Just can give me one more example. Give you such a easy. Can you talk about one application? Anybody? Let me see in the chat box whether anybody is posting. No, I think. Let me talk about. It's not only mental state analysis. We can talk about lie detection. We can talk about the IQ of a person. But the IQ, we refer to the IQ of a person, not only the IQ of a person being identified by asking him to attend a test or some competitive exam, whatever it is. Then, based on the score, what happened, we are going to say his IQ is something by just asking him to perform certain tasks. But when it comes to IQ, normally IQ refers to what? IQ refers to the cognitive behavior, cognitive intelligence. It is not like that somebody 6 feet is more intelligent, somebody 3 feet is not. It's not like that. So IQ, when it refers to the cognitive intelligence behavior, from that comes from the human brain. IQ actually is a indirect or direct, it's a direct behavior, that direct parameter related to the human brain. So why I say some asking to take some test or some kind of skill test something, I just directly get some brain signals, try to say whether his IQ is something or not. So such an application can do. And even I can say, no, let me continue with it. Now, so these type of signals we are going to connect with the human brain activities, behavior analysis. But when it comes to the data acquisition process in the brain computer interface, you have to understand there are certain experimental protocol one need to follow. Normally, EEG signals when we are collecting, we normally follow invasive and non-invasive mode. Some of you are already aware of this, but the beginners when we talk about, please be cautious about this. And of course, eventually we are not going to make any surgery or operation to make some complex signal acquisition. That normally be performed by surgical and some surgeons or some neurologists or some medical practitioner for the selected healthcare application when such a surgery is involved and when they want to see the brain behavior. Otherwise, in normal cases, like applications like lie detection and others, normal applications, IQ testing, you can connect the brain signals in a non-invasive mode. And where these doctors and practitioners and all those others do like invasive mode for these complex collection of EEG signals directly from the human brain. Otherwise, normally we go for non-invasive mode. In non-invasive mode, what happens? We are going to connect the electrode directly on the scalp. See the different layers of the brain. Initially, first we have scalp, then periosteum, sulcus, dura mater, and subdural space, and all those things. Finally, we have the human brain. So there are about 5 to 6 different layers we have, under which the brain is safely located or placed. So when we talk about such a complex application is to be conducted, we have to make sure that the signals are being captured in a non-invasive manner, unless complex typical medical application is involved, that is to be performed by the doctors. We normally go non-invasive mode, where we are going to place the electrode on the scalp of the head. Then we are going to connect the EEG signals, the summed iconic currents, which are being emitted from different neuron communications. Okay. And problem is like what and all the signals we are connecting. Most we do for non-invasive mode, that's it has different layers of brain. The quality of signal is not so good. They are very weak. Therefore, we may require to amplify the quality of the signal. Therefore, a typical amplifier is being used. Normally, they try to amplify some 1,000 times or 10,000 or 5,000 times, and then. So normally the signals which you are trying to capture in a non-invasive mode, we try to amplify some 7,000 times and then filter them. That's how we are going to capture. If you can see the figure, you can understand that is to make sure that in a safeable, or you can say a reachable state, the signals are being captured here. So when you perform these activities, please be cautious. We are going to use non-invasive mode. It's very clear, and only such an application we are going to identify. The application which require invasive data acquisition of EEG signals, to be very all the experimental protocol to be followed. Here we have to take consent from the Institute Ethical Committee, where the Institute Ethical Committee is going to detailed proposal, what you are going to do, which type of data you are going to collect, what you are going to do with the data, and what is the outcome. Then if all the things are convinced, then they are going to say okay to your project proposal. Otherwise, no. So unless you get an ethical committee approval, you are not going to, you're not allowed to do such a research or such a data collection. Fine. So ethical committee approval. Then once ethical committee approval is done, also we have to take something called informed consent. Informed consent. That's from consent from each subject from whom you are taking the signals from. Following me, it is very important. These two protocols to be followed very strictly. And if this is only like normally this informed consent when we talk about this for humans when we do. If you want to make some cognitive analysis applications for animals, assume that because animals also have brains, right? Then what you have to do, you have to follow little this ethical committee approval, but informed consent may not be needed. Why? Because animals can't sign, right? They cannot sign. But when it comes to humans, this informed consent by the person whom you are taking the data, they're known as separation, whatever it is. And then the ethical committee approval, both are needed. Just follow them very critically because they are very important to avoid any later stage problem. Don't think that it is just a non-invasive mode, therefore we need not cut the brain signals by taking the cons and nothing will happen. No. Because it's very crucial the subject, though it is non-invasive, anything happen to the subject, finally the brain will come to you. When it comes to the entire brain-computer interface system and how the application can be established, this is how we say set up complete interface. There is a subject or patient according to the type of application they are investigating. Normally, when we talk about this, some simple application like lie detection or some IQ test or IQ measuring, whatever it is that system, and then any other simple application, mental state analysis. For such simple application, you can call them a subject. For some medicinal application, some healthcare application, you can call them as patients, whatever it is. And finally, there is some front-end device or your application device. By collecting which signal you are going to control the device. Maybe a smart wheelchair for a paralyzed patients. Paralyzed person who cannot move or walk, who want to control the wheelchair, or thoughts, or who want to control the home appliances or some IoT appliances in the home, like smart AC or smart refrigerator, smart lights, everything. They can control with their thoughts. They need not have an assistant, like something like that. Not exactly. So the brain behavior is being captured and understood and then analyzed. After that, we are going to make some automation or control of a front-end device by using the suitable machine learning model here. This is how a typical a feedback system or communication system look like. There is some EEG control unit. There is an amplifier. There is a feedback screen. There is a workstation or a high performance system according to the type of data and number of channels and all those things, of course. Then some suitable customized software tools for the recording and analyzing purpose of the EEG signals. So normally what we do, we collect the brain signals from the subject. The signals are sent to the amplifier. Amplifier will send the amplifier, these control signals, actual signals, the filter signals to the computer, or you can say the workstation. And there is a feedback screen is seen based on the signal, whether the signal quality is okay, so on so, and whether the subject need to be stabilized. Or again, you can have another trial. Normally, subject 1, trial 1, subject 1, trial 2, subject 1, trial 3, and so on. And similarly, subject 2, trial 1, subject 2, trial 2, subject 2, trial 3, and so on for subject n. As many subjects as you require. Normally, 10 to 20 subjects is enough for a simple application. Some other complex application, you may have to validate more on a more sample. You may have to have more subjects. This is how, and there is an easy control unit who is going to control the entire, the collected signal via the amplifier and based on the input parameters and set by. So this is normally TTD, feedback and communication system for collecting the brain signals. There are some sophisticated tools exist for this one. For data acquisition, storage, and signal processing, everything. Classification by default, obviously. There are some existing supervised and unsupervised learning tools are existing there. And these filters and some other normal tools exist for this one. But this changes from make to make and company to company. Yeah? This depends on normally when you buy an equipment from certain make or a company of certain model, normally they have certain type of electrode wire, certain type of amplifier and all, and suitably the recorder and analyzer softwares or tools they provide. When you go for other type of hardware tools, again they will provide their customized tool. They may not synchronize to every hardware what they are going to use. Right? Now, when it comes to the type of application which we like, some healthcare, now we have seen a lot of other application like lie detection, human contemplation, mental state analysis, IQ test, and all, etc. Similarly, some biomedical application, normally some neuromodulation, where we are going to take the signals and use it for some type of problems in the human body. Normally, when we talk about this neuro, there is some spike or something happen when they say this central nervous system or something not being active or not it is being affected because of so. So we can make such interface and try to connect the brain signals and try to rebuild the system, just making a device like that. So there are normally 3 types of neuromodulation, like deep brain stimulation and transcranial magnetic stimulation and vagal stimulation. These 3 mostly we learn like TMS related and DBS related. Third one is most medical, highly difficult. When it comes to deep brain stimulation, normally we are going to place an electrode inside the brain. It's very, very important. Inside the brain. So this is not non-invasive. This is invasive mode. We are going to make some small surgery or whatever it is, and placing the electrode inside the brain, maybe onto the brain, whatever it is, but opening the skull. And where there is this electrode wire running down somewhere in the body, where we are going to have battery pack or something. And these things, why we are going to use like there's some Parkinson's disease, epilepsy problem, or some stroke issues, and all those things. We have to control the performance of the human brain or the behavior of the human brain, the cognitive behavior, by sending some input signal from here and by capturing the brain signal, something like that. Some analysis we are going to make at the end. So, and to deal with some compulsive disorder where the person is under pressure or some psychological issues, all those things. The research is in the beginner way, but of course, there's still a lot to go. But of course, since it's the invasive mode, there is some infection like surgery and all those. That's not our best from our point of view. When it comes to transcranial magnetic stimulation, and we're going to make some application of some magnetic field. By doing so, we're going to induce some electrical currents, and which are going to make some influence on the human brain. But of course, it's non-invasive mode. It's non-invasive mode. Only thing is like it's like wait and see method, where we are going to capture the brain signals of each and every trial and how they are going to affect, or you can say influence or improve the function of the human brain for certain cases, like the person is very drowsy, or you can say he is very dull, he's not very active, and we are going to make some correction, like all these things. So how it is going to work? We are going to have the magnetic pulse onto a certain region of the human brain. By doing so, we are going to make the person to ease the depression and get rid of his, negative thoughts and all those things. So that normally, like we have seen, if you go back to the behavior of the human brain, like we have four lobes: frontal, parietal, temporal, and occipital lobes, and each of the lobe, what is behavior, we have talked about already in brief. And we know exactly which portion of the brain, which lobe of the hemisphere, which lobe of the which hemisphere exactly has the problem of so and so, right? Therefore, if you know that the person is very dull, the person is not active, the person is having certain problem, etc., if you can make such a non-invasive procedure where we are going to project the magnetic pulse to just make certain brain cells in that particular region to act to be active, so that we can control the mood of the person. So all these things can be possible, but there is it's a lengthy procedure, like it's not a one sitting or not. Normally we are going to use the treatment device, and you use it for certain times, maybe some certain short intervals for a while. Then we are going to ask the subject to react accordingly. Then we are going to collect the brain signals from the subject, and we are going to see each of the person. We are going to see who has taken this treatment. We are going to see the clear what exactly the improvement in the human brain, uh, by way of making such a magnetic pulse to be imposed on the human brain, so that we can see. But based on studies and benchmark results, it has seen that such a therapy has certain positive behavior impacted on the human brain. But there are some issues with the human brain. This type of TMS type of application. Well, here only surface structures of the human brain can be targeted when it comes to. But anyhow, it's again medical issue when it comes to. Similar some IoT application, when you talk about a smart healthcare IoT system can be established or developed. Neural processing and neural rehabilitation type system we can develop, where we are going to replace a particular human limb with, the missing limb with a particular IoT, smart IoT device, healthcare device, uh, by just taking the thoughts, or you can say the signals from the human brain, or the muscle receptors where the signals are being carried forward via the nervous spark. So, if you can see how the spinal cord abridges the communication from the brain to the entire central nervous system, if you are going to observe where exactly the missing limb is there and how the signals are not being captured properly, if you can see, and if you can bypass the signal to a particular external device, we can make wonders, right? Like we can make an artificial processing device to be developed like this, which work almost like a natural one. Please, you have to try to understand. This is not like a normal other prosthetic device, like that wood one or whatever it is. It is completely different. When you take the other one, it's even its weight also the particular person has to carry. When it comes to such a smart prosthetic devices, when it is taking the signal or lifting a particular leg, it can capture its weight, and accordingly it can generate certain force from the foot point of, so that it can have certain linguistic moves can be generated, where the person feel like he has no artificial limb. Not exactly, rough idea. Similarly, this retinal implants, when we talk about in the human computer interaction, where the person cannot see, there is some problem with his cornea structures are, so maybe you can have some artificial chip placed in the inside the human eye or close to that, and there is a the real-time images are being captured by the lens that are, the artificial lens, and the chip is connected to the optic nerve, which is directly connected to the human brain. Via the optic nerve, the signals or images can be captured or read by the human brain. It's not exactly, but almost a similar, like artificial vision system is being developed with such a retinal implant. But this research is very, very, very tiny stage, and there's a long way to go. And there are a lot of problems with the neuroprocessor devices, of course. Whatever the type of we have. for positioning the device, where to implant, and invasive, non-invasive mode, and making them work in the real time. And every time they have to start on startup, they have to reprogram. They have to, see how exactly to process this. And most important challenge here is like information processing at real time, speed of information transfer, and then feedback delay is another challenging problem. And poor signal quality, sometimes the signal may not be captured for whatsoever the reasons are. So all these things are the challenges. There are some people who have used such a cognitive science related systems and how they have survived for years. And when it comes to the EEG, like I already pointed out, why EEG is like why people are focusing more into such a complex signals using human computer interaction. They were not there in the beginning. Yes, it was very easy in the long back, like close to 1930, 1929. People have observed there is some electrical field is being reflected around the human brain, and they've understood some kind of waves or magnetic fields are being captured. Electrical fields are being captured by default. Then they have seen there is some particular subcortical structures of the human brain are to be understood or analyzed further. But unfortunately, that time there was no computing power, there was no much memory management systems. It could not be fully utilized. But when it comes to now the last decade or 2 decades time, where the computing power has been drastically improved, people started refocusing on this such a complex brain signals. Now, when it comes to the understanding of the human brain, because if I want to use some unsupervised learning model, supervised learning model, first I have to understand the type of behavior of the human brain. Like I've already told, some benchmark signal. Like you see, if I take some supervised model, I'll just say, okay, this is the behavior, this is the signal, these are the values, this is the discretized signal, and finally this is a class level attribute. How I'm going to, first of all, I've trained my model, right? To train my model, I should know all the supervised information like this, right? So no, there are a lot of like normal brain. No, these are not the only waves we are going to have in the human brain. Different type according to the type of task or application they're performing. Normally we have beta, alpha, theta, delta, and other type of signals we have. When you talk about beta waves, normally they are seen when the person is alert. And when we have alpha waves, normally we have seen when the person is, when the subject is relaxing mode. Theta waves are generated normally when the person is sleepy. Similarly, light sleep, we have different type of representation in signals. Deep sleep, we have delta waves, look completely different compared to the other type of signal, alpha, beta, theta. Simply dreaming, or you can say paradoxical sleep. Paradoxical sleep is nothing but dreaming. When a person is dreaming, we normally see REM type signal. If you can see, they are all different compared to the other type of signal. So our job is to understand in depth all these type of behavior in the human brain. And when it comes to the comparing or you can say analyzing, it is easy for us to use any machine learning model, right? If you go with such a complex understanding. Now, by just making such a data acquisition, it is easy for us to make this application, right? Now, beta, alpha, theta. Can somebody say one application using these brain waves? Let's stop. Unless you answer, I want to go. Tell me. Just one application, somebody using alpha, somebody using beta, somebody using theta, like that. Can you develop a small application using this one? Just try to guess, anybody. You can unmute and answer. I said the session should be interactive, nobody is speaking.
They have understood completely or huh? Reddy,
Yes.
enough speaking.
Sir, please.
Sir, to estimate whether the person is lying or not, for that application it can be used.
Yes, that is one. But see, when we come to normally that makes the difference. Now, when it comes to the like normally the behavior when we are picking, like picky behavior we take from the human brain. if it's in a beta alpha, or you can say theta beta, I'm going to talk about. What I'm going to do, if a person is driving a vehicle, assume that I'm going to make a smart, like easy cap type application. There is a wearable, or you can say wearable IoT type device is connected to the human brain. Just a easy cap. A person is wearing a cap or something. I'm going to have wearable EEG signal. I mean, wearable some IoT device type, small electrode with 1 or 2 electrode device, wireless. They're wireless wearable device. So they're going to connect the brain signals on real time when the person is driving the vehicle, and when the person is driving the vehicle, normally which type of brain waves you want to see? Tell me. Can it be like when we see theta waves? Now see, if you can see every vehicle has a processor. Like now, if you can integrate a particular vehicle and its what you can say processing system to this particular EEG system, or you can say IoT system, and you can integrate and say that what if there is a scene of theta waves, the person is sleepy and the vehicle should not move, and unless the person is relaxed for some time, and unless we see the presence of beta waves, the vehicle should not move. So can we make a smart vehicle management or vehicle control system that is, you can say EEG controlled, or you can say EEG based control system for vehicle management, something like that, not exactly, something like that. A smart safety system we can develop, right? Where drivers' brain signals are collected on real time. There's a smart wearable device. I'm going to show the wearable device how they are going to look like in the next slide. They're not very expensive even. They're very expensive. I mean, they are not very expensive. They're about 18,000 rupees for one electrode. So if you can make such a small real-time signal with some battery wise, then what happens? It is easy for us to observe the person, and even in fact, not we, the owner of the vehicle sitting in the house, they can see over a wireless medium. If it is connected to internet, you can see that no particular driver is sleepy, but he's still driving. The vehicle is going. You can send a message to the driver: you are sleepy, take rest or come back, or whatever it is. This is one such application. Just I'm not similar to that many. Now, when it comes to lie detection, there are some other signals. I'm going to show like lie detection. When we come into like alpha, beta, and normally like when the person is lying, normally should be relaxed, and when he's not lying, normally we should see some alpha waves and some other type of waves, P300 and some other type of signals to be seen. So compared to that type of application, this type of application is more suitable. And similarly, if you want to see the concentration levels of the students who are preparing for the examination, and other applications, other safety applications, or any other application where this alertness is to be needed, something like that. But each of the signals has certain ranges. When you come into beta, we have 13 to 30 hertz, and normally they occur in frontal and parietal lobe. When it comes to alpha, 8 to 13 hertz normally be seen in occipital lobe. That's what I'm saying. It's very, very important to understand, though it is not a biological class, you have to compulsory understand the inherent structure of the human brain, that is cognitive behavior, by which you can see, okay, I'm going to find for the driver safety application, some smart control EEG based application, but which signals I have to take? I don't know. My problem statement is good, but I don't know how to solve. So it's very, very important what type of brain signals I'm capturing, whether I require beta type signal, I require alpha. If I require alpha, where I have to collect, I should know. Normally alpha waves are seen in the occipital lobe, and similarly theta waves are seen in these children and sleeping adults, and certain type of lobe structure of the human brain, and everything we have to understand very clearly. In fact, now the same we can use for a dream analysis. As normally when we say a person is dreaming, normally if you ask a person, he is the only person who can say next day that I had a dream. Nobody can say. And if I ask the same person whether what time you have had a dream, he cannot say. When the same person who had a dream, he cannot say what time he had a dream, because normally we remember that we had a dream, but we don't know exactly what time we had a dream. But if we are going to connect an electrode wire before he is going to bed, and next day we can say, I think we have seen the REM type signal dreaming. You must have had some dream, and we can say the time also from 3:30 a.m. to some 4:30 a.m. we had a dream. Can you imagine from where to where we are going? So such a level of research is possible, I just want to say. So whether it's a dreaming analysis or what another application, that is different, of course. But such a level of research is possible. In fact, We can also talk about like finding the ATM pin number of a person. Is it possible to find the ATM pin number of a person? Tell me. Without asking him or without the person sharing the information. It's very difficult. Normally what I can say, like I will ask the person like, what is the first digit of the ATM pin number? How many options we have? Tell me. Somebody? If I ask, so tell me what is the first? It's 0 to 9, right? Somewhere around 10 possibilities, right? Am I right?
But is it possible to even track that numbers?
Can you repeat? I didn't get you.
I feel it is not possible to track the numbers.
Yes, not the part, not right. What I'm saying is, now let me just spend 2 minutes time. I will convince you that it may be possible. How it? I'll explain. Now ATM pin number has how many digits, madam? Normally
Usually
4 digits,
four.
right?
Yes,
4.
yes.
First digit, how many possibilities are there?
9 possibilities.
Maybe 0 also. I think if we first is 0 to 9, maybe 10. Assume. Okay, worst case. Okay, so second digit some 10, 0 to 9. Third digit 0 to 9. Fourth digit. So I will call the subject from whom I want to know his ATM pin number. I will ask him to see. Then I will ask. I will show a slide 0 whether it is your ATM pin number, first digit. Then 1 whether it is the first digit of your ATM pin number. Then 2, then 3, then 4 up to 9. Now, how out of 10 questions, his brain knows which is one correct and which is wrong. How many positive and how many negative reactions you see from the human brain signals? Somebody tell me. See, when we show the 0 to 9 numbers, brain knows which is correct, the first digit, because it is his own ATM pin number, right? So out of 10, how many positive, how many negative?
One positive.
Signals, just a minute. 1 positive and 9 negative signals brain will emit, right? Are you following me? So for 4 digits, there are 40 questions. Out of 40, 36 are negative, 4 are positive. Do you agree? No, my question is it not a classification problem? Is it not a classification problem? Now we have 40 signals where 4 are positive, some 36 are negative. Is it not? Next thing, is it possible to make such a micro level classification where we see the brain behavior? And yes, of course. But accuracy matters, of course. Why? Even if you can make a blink of your eye also, we can reflect the difference in the brain signals. We have done that and we have shown. Unfortunately, it is online. Otherwise, I could have called one of you here and show that even if you blink your eyes, we can show that sometime you have blinked your eyes, this is a signal being captured. That much, micro level, classification we can perform in the brain signals. It is possible. But problem is, same time, some other artifacts, some noise signals will come into the picture. And when the subject is tense, he may give different spikes in the human brain. The brain may give. So also we have to make the proper analysis, and that's why the subject need to be stabilized. We have to train the subject for some time, of course. But I don't say it is impossible. Even if you talk about a prosthetic arm, like the person with a missing limb, if you go with artificial limb, it is closing and opening, that's closing and opening. This is a binary classification, support retribution, or whatever it is you can use. Right. So it's a binary classification. So it is like what? 1, 0 and 1. When you close 1, when it is open, it is 0, something like that. Same, it is like one is positive, one is negative. It is not very difficult or impossible to extract, or you can say segregate such a positive behavior from the negative behavior from the human brain. Because one is for negative, they're different. Certainly they cannot be one question, one is right answer, one is wrong answer. They cannot be same, right? When there are two different signals, it is a matter of time to segregate them. So I don't say it is impossible, but not say possible. It is there, but not so easy. Because making such a level of, classification or learning is not so easy, but it is possible. It is possible really. Now, if you can train the subject and if you can understand his brain signals for a while, if I show the subject these 10 digits for each, 10 numbers for each of the digit, at the end of the day, we can approximately say this might be his ATM pin number with different combinations. One will work. I'm saying it is online. Otherwise, I could have shown you. Even if you blink your eyes, also I can say, see, sometime you have blinked. This is your signal, brain signal. Brain signal changes even if you blink your eyes also. But question is where you take the data, which channel, which part of it. That is very important. For that, you have to understand very well. I mean, of the functionality of the human brain. But of course, I didn't say it's so easy, but it is not impossible. Approximately, you can do. So there are plenty of such applications. This is the whole operating. I mean, the entire operating environment of the. If you can see the front end device is like some smart wheelchair we are going to develop, or we are going to control with the help of the electrode wires connected to the human. I mean, with the help of the EEG signals collected from the electrode wires connected on a particular subject or user, who in turn connected to the amplifier. And the amplifier is connected to, there is the control unit, user control unit at the BCA level for feature extraction, translation, of course. So once the features are extracted from this one amplifier, those features we are going to use for the control interface. Based on the control interface, and there is something called semantic control. By just taking the repeated signal different trials, we are going to see how they are going to work. There's a device controller. This device control, when it is sure of what exactly signal indicate, it is going to ask the device to work according to the input signal that is being generated and emitted from the brain, which is pre-processed in due course of time. Are you following me? So this is the overall operating environment of the human brain, how they have been captured. So here the machine learning part when it comes to feature extraction, dimensionality reduction, deep learning, stack of autoencoders, swarm intelligence, fuzzy logic, type 1, type 2. Type 2 mostly opted here. Feature translation, classifying signal, then device controller, decision making you can use. Everywhere you can use. Regression analysis you can use here at the same time. So the same thing what I explained, like different machine. Similarly, for lie detection, there is something a P300 speller. Normally, when we observe such a 6x6 matrix for some particular stimuli behavior, normally this try to identify when to a specific output. Normally, to a specific output stimuli, we call it as. Normally, we try to, recognize the stimuli when we see the same object again. A similar object exists in the human brain. When there is a matching, or you can say pattern matching type problems, we can use lie detection. Now, if there is a person like who was sentenced to, not sentenced, who was identified as a suspect in a particular crime, or one or two person, maybe you can call them and interrogate. Like you can show the crime scene photos like weapon used, person photo, that person murdered or injured, and then crime scene photo where which block or which building it is at, and all those things. If you show, if there is a innocent person who has not seen them, maybe you may not be able to see the presence of P300 speller, and the person who has used it, because the similar stimuli already exist. Similar stimuli. So since the similar stimuli already exist in the system or in the memory system, the person may be identified with a P300 speller, and he may be identified. You can doubt him, something like that. It may help him in the interaction process and all those things like that. So question is like I already mentioned, finding the location of the human brain where you really want to take the signals. That's very, very important. Now, if it comes, I've taken some 4 signal for a specific application, maybe light detection, whatever it is, T78, P7P8. Means what? This particular channel will indicate better behavior when it comes to such a application. Like somebody is like mental state analysis. These 4 channels give crucial information, crucial brain signals, indicating the application. So there are altogether more than 250 to 260 channels exist in the human brain. Our job is to identify. Of course, there are multiple channels in different. In one globe. In game playing also we're going to use how the BCA work for some game playing applications, and some control this virtual and augmented reality application, and then some control activities. Like I mentioned, non-invasive BCA, this is about, mostly we talked about The one that is shown in the cave is the easy cap in the first figure, which we are going to connect with a lot of electrode wires, and the signals are being captured. Like I mentioned, the wearable EEG device. It is easy, like we can use it for some virtual patient monitoring system. A person has undergone for some psychological problem. Now he looks okay. So we are going to discharge him, but I want to have a track on him. Maybe you can ask him to wear this 24/7 or sometimes at least in a day. Then we can have an observance or you can say surveillance over the person, and we can see based on his real-time EEG signal, the person looks normal or he is likely to go abnormal again. Maybe you can ask him to come back to the hospital or whatever it is, just like that. So some wearable systems. So there will, like I mentioned, the driver application, smart, vehicle management system, and all those things. If you can see how the persons are wearing this such a wearable EEG device, and which are interconnected, which are connected over a wireless medium, and used for application game playing, virtual and augmented reality, distributed virtual reality, this distributed game playing, all those things. Then similarly, this smart application, where and all you require wearable devices and game playing on same. Similarly, future when we talk about, like I already talked about, plenty of other applications are possible, but same time lot of ethical issues will also come into this domain when we talk about, because this domain, like when it comes to very high level of research happens in this domain, it becomes like no, previously if we can talk about like swiping a card, a magnetic strip card, then we have a Wi-Fi reader cards, like say you can, now we have like Wi-Fi card. When we come, you need not to swipe it. If you can take it close to the swiping machine, you need not swipe it, it will automatically read the signals. Now it is like that exactly. Now we are, some people are misusing. When you are holding such a credit card with such a, I mean swiping, what you can say, that reading chip, if I can take the swiping machine close to you, I can get whatever the amount I want to withdraw. So it's very, very important. These ethical issues will come into the picture. If I can grab somebody crucial information, privacy information for somebody's human brain, because when machine learning is there, when your data is in your hand, analyzing and predicting is not so easy. At the same time, not so impossible. So therefore, with the development of advanced machine learning model and high-end human computer interactive systems, it becomes possible to break all such ethical issues. Therefore, now these problems will come into the picture: privacy and secrecy and all those things. Not only that, even healthcare side also. Healthcare side also, a lot of other problems will be there. And but any application that is solving being solved here, that has a lot of impact, lot of influence compared to other, like for example lie detection. If I can develop a BC application using some advanced machine learning models, maybe deep learning or whatever it is, uh, optimization algorithm, whatever it is, if you can find with 100% accuracy somebody is lying or not, all the court cases get solved in a single day, right? Our question is how to make such a highly accurate model based on the brain signals captured using some advanced machine learning model. People got up to 1994, but not 100%. Therefore, it can't be used. So, such a, drastic applications it is going to be resulting in. That's why this domain is unique compared to other domain. And without machine learning, it is not at all effective. And where and all I can use, like, is most of them are training and learning type problem. Neural networks you can use. Otherwise, you can use like genetic algorithm, fuzzy logic, farm intelligence, bias for optimization algorithm, rough sets, information sets, fuzzy theory, everything it is open to, depending on, because most of them are supervised and unsupervised learning models we are going to have. So that's all from my side. If you have any doubts, let me know.
Hello, sir. Good evening. The presentation was wonderful. Thank you so much for the presentation, sir. Everybody,
Yes. Any
the
doubts?
panelists, yeah, that's what, sir. We'll wait for a minute. If anybody has any
Yes.
doubts, you can please ask, or you can post it in the chat box as well. We'll wait for a minute, sir.
Sir Reddy, good evening. Annappa here.
Sir, good evening, sir. Please.
You're discussing about detecting driver alertness and things like. Okay,
Yes.
driver may be alert. He can't make out whether he's sleepy. I can make out. But the thing is, sometimes the driver will be driving. From outside, looks like he is alert. But something is in mind. Something happened at his house or something is in mind. He is not able to concentrate. Is there any signal you can capture regarding this status?
Sir, now see, when it comes to mental state analysis of a
Yes.
person, normally, like I already mentioned, certain type of waves, like you can say beta, alpha, when person is relaxing or alert, we are going to have certain type of behavior. Similar to that, every emotion related, there are different signals. I'm sure sampling, just for a sample, I have shown 4 or 5 signals. For every behavior, every emotion mood, there are different type of signals being captured.
Okay.
Now, when it comes to a particular person who is driving or who is managing a vehicle, what we need to do, the person has to be, first of all, it should be a real-time device we are going to develop, sir. Real-time device which we are going to place on the inside the vehicle, which is connected to an electrode wire that is placed on the person head. If it is the wired system, the person cannot drive properly, you can make it as a wireless device. I have shown in the last slide, there is a wireless device.
Okay.
Like he can just keep it like a small headset. Nowadays, if you see 24/7, people are having headset on their this head.
Okay.
So you can make such a small wearable system where it is going to connect the EEG signals in real time for 1 or 2 channels is enough.
Okay.
Then they can be transferred over a wireless medium. Then the vehicle itself will not start unless the person is in a ready position to drive.
Okay.
But that's why it should be a real time system.
Okay.
It should be real.
Starting, he was okay. He started and he drove for half an hour. Now something he saw, so suddenly it came to his mind about his family or
So
something.
once such abnormal behavior is noted from the brain signal,
Uh-huh.
immediately the device is active and it will send a message to the vehicle, because every vehicle has a processor, right?
Yeah.
Now the vehicle is not. It is going to stop all of and say you are not in a position to drive.
Okay.
Or first it will give an indication, like now, if for example, if you don't wear a seat belt, obviously there is an indication. Similar way, there will be an indication. Same. It's the vehicle driver, or you can say alert system, something like that.
Okay. Thank you.
Right. I think there is some question from Rajesh Kamath. Can we capture a distracted driver detection like taking our phone while same answer we can do it here as well. Now, that when somebody is if you can see, when somebody is speaking over phone when he was driving, if you can see, when somebody is speaking means his hearing function is more active. When hearing function is more active, if you can see, when you are hearing a lot of things, other functions becomes like dull, or you can say inactive. Like when I'm hearing more, I'm talking about a mobile, I cannot type much. So based on such a deviation in the human brain signal, you can somehow make a differentiation of that classification, and you can capture same just, but signals may be different. That's all. Okay. Any more doubts? If there are no doubts, we can wind up.
There is one more question in the chat box, sir. Can we capture
Yes.
distracted driver detection? Can we capture
same I have answered.
distracted driver detection like talking over phone while driving?
This is the same I answered, Jay, just now. After Annappa sir, I answered the same I answered. It's the same question, but it's the different. Now, when we talk about this, like somebody's, now see, that is actually simple logic. Even further, we need not have an EEG, machine or something. We can simply have an Android application that is connected to the vehicle management, the processor, whatever it is. Once the phone is ringing and the phone is active or the person is speaking, the vehicle will not start. For that, we don't require brain signals to be captured, if you may agree. That can be solved with a simple Android application where the Android phone is interconnected to the vehicle. Right?
Yeah, we got it, sir. Thank you so much for answering the questions and the session, sir. I think now Rashmi ma'am can take over for the vote of thanks.
Thank you, Shubham. On behalf of the organization and participants, we would like to extend our heartfelt gratitude to our esteemed guest, Dr. Damodar Reddy, for delivering the talk on concepts of HCI, PCI, and its application. I'm sure participants will make full use of it. Thank you, sir. Please accept the virtual vote of thanks, sir, on behalf of the workshop. Thank you, sir.
Yes. Thank you, madam. Thank you.
Thank you so much, sir,
Yes, thank
for
you. Thank you. That's
accepting
all.
accepting as a speaker for this session from your busiest schedule. Thank you so much, sir.
Thank you, ma'am. Anytime. That's all.
Participants, I'll be sharing the link for feedback in the chat box. Kindly provide your feedback right now. For all the 5 days, we want the information. I'll be just posting in a minute. I hope the link is visible. Please provide the feedback for the certification. It would be required.
I think that brings us to the end of the 5-day workshop, right?
Yes, Samarth.
Yeah. Thank you, sir, for coordinating. Thank you, Bhavna ma'am and Shubham, Marabi, and everyone for coordinating from NITK side. It was really nice organizing this workshop in collaboration with IEEE Young Professionals and NITK IEEE Student Branch. Looking forward for more such collaborations between the two organizational units among IEEE.
Thank you, Samarth. We at NITK 𝗙𝗿𝗀𝗃𝗃 want to thank all the officials from IEEE Bangalore section and IEEE Bangalore YP, especially Bangalore Young Professionals Society, where our own alumni, Samarth Bontala, is one of the Execom member. He supported us through Bangalore Young Professionals to get this get our proposal approved and get funding from Region 10 Young Professionals through IEEE Bangalore section Young Professionals. So I wholeheartedly thank on behalf of NITK 𝗙𝗿𝗃𝗃 IEEE Student Branch for supporting us in conducting this 5 days event and giving us some of the top speakers to attend this. So it is a combination of both academia and industry. We had 2 speakers from industry and 3 speakers from academia. Hope all the participants who attended this workshop for the last 5 days benefited a lot. I request all of you to take it further in case if you have any doubt or clarification or some research aspect you want to take it further. Feel free to interact with these speakers. I think most of them will respond to you in a day or two because they are busy professionals working. So wait for a day or two. You'll certainly get a response from them so that you can continue your research journey. That's what our aim of this workshop. In this, I thank all the persons who supported us directly or indirectly in various aspects. Thank you, one and all.
Thank you,
Thank
sir.
you, sir.
Kindly fill up the forms and rest of the certificates will be sent to your mail IDs. In a day or two, you will receive your certificates through mail. Okay. Thank you all for attending the all 5-day session although it was raining, some have come in person as it was in hybrid mode. So thank you to all the participants who have taken part in this workshop, as well as to the research scholars who have supported to make this workshop a grand success. Thank you all.
Thank you, Anapa sir. Thank you, Bhavna ma'am. Thank you, Samarth. Can we conclude?
Yeah, you can end the recording, Shubham, and then you can conclude. Yeah.